we're going to continue on sequence-to-sequence models, and attention. But make sure to sign into the attendance poll number 1225, right? Now, here's the problem we were talking about in the last class. We want to convert one sequence to another, where there may not be any kind of correspondence or any expectation of a correspondence between the input and the output. You may not have symbol level correspondence. In fact, the output may look nothing like what goes in, for example, in a dialog system. So we saw that this was an instance of a model such as this one, a delayed sequence-to-sequence model, where you would have to analyze the entire input, and then based on what you have seen in the input, you would generate the output. So this had two components. The first one processes the input to generate a hidden representation for it. And that was the, so when the entire input has been processed, the final hidden state captures all the information about the input. And subsequently, the second component of the system uses this final hidden state as an initialization to go ahead and generate the output. And the problem over here is that if you went about it naively, then the word that you generated at any time would bear no relationship to the word that you generated at the next time. So we wanted feedback. So each word that was generated went back in to assist in the generation of the next word. And this was basically the concatenation of two types of models. One was an encoder, but what the generating system, what did we say it was? What was this? The decoder, but it was a language model, right? So this was just a so in essence, we have created an encoder to derive some information from the input signal input, and then use that to as an input to a language generator to produce the output. Can you shut your laptop there? Don't make me ask you guys ever again. Right? So, and so this was what we call the simple translation model, where you had the input which went in, and the input was analyzed, and we got a, what happened here? Hidden representation out here. That was this one. And this hidden activation at the end of sequence marker for the input stores all the information about the sentence, and this was then sent to the second recurrent network or decoder which generated the output, right? And now the output, of course, the decoder, of course, produces the output one word at a time. So this is what was called the terminology for a model such as this is an auto-regressive model. It's auto-regressive because it's using its own output to generate future outputs. So at the very first time, you generate, you'd compute a probability distribution and maybe draw a word from it, say ish, and that word goes back in to generate the next word. So it's regressing on its own outputs. This is an auto-regressive model. And so you'd regress like so until you generated the final end of sequence marker. So this was the model that we saw in the last class. There's a problem with this model, and that is this, that, okay, this was the encoder and that's the decoder, right? The problem is that all of the information about the input is being compressed into this one little representation at the very end of the sentence, into a single end of the input, a single hidden vector. So this one is kind of overloaded, right? And what are the drawbacks that one could see with something of this kind? Anybody?
Information loss.
Information loss. What kind? So as you keep going forward, you're aggregating more and more information, and there's always going to be a recency bias, right? So it's going to be remembering a lot more about the most recent words, and the stuff from the very beginning is going to get forgotten. And the longer the input gets, the harder this vector is going to find it to actually represent everything about the input, no matter what kind of model you use on the encoder side. And the fact is, if you consider the output over here, every word in the output actually relates to some specific portion of the input. Then it's never more apparent than when you're trying to perform translation. Say if I'm trying to translate from English to German, then what you find is that each word in the output actually has the closest association with different components of the input. So in reality, all of the hidden values carry information, and this is going to get diluted by the time you get to the end. So if you look at the actual associations that you would find that are most pertinent, the word ish is best associated with the word I, right? The word Apfel is best associated with the word apple. And you're smooshing all of these into the one representation in the red box. So this correspondence that actually exists is being lost. So how do I generate a representation where all of the elements of the input are equally well represented? So the problem with this mechanism is that by the time you got to the end, the words at the beginning are maybe underrepresented, right? We want to have all of these things be equally represented. So what would one example be? How could you do that? But if you feed everything in, you have no idea how long that model is, the input is, right? So what else could you do?
Weighted sum.
You can average or weighted sum. So the simplest thing is say, I'm just going to average everything, right? And then you average everything. How did that happen? So I'm going to say, no idea. All right. So and again, when you compute the average of this kind, it's not sufficient to just feed the average to the decoder at the very beginning, right? This must go in at every time. So this average vector is no longer just being sent in out here. It's actually going in at each output, because each of them has to refer to the input, right? And if you just feed it only at the beginning, by the time you get to the end of the output, it's already forgotten much of what went in. Yes?
If we just take the average, don't we also still lose the information from each of these?
Yes, we do, right? And so what we want, just taking a simple average, is still losing information in the sense that when you look at something of this kind, then the fact that ish is better related to I than it is to Apfel is not really being considered, right? They're all being given equal weightage. So you want to have a different weighted sum of all of these input representations going in to the decoder at different times. So for each of the words, ish, habe, einen, Apfel, and gegessen, in the production of each of these words, you would get a weighted sum of the hidden representations for each of the words in the input. And the weights would be different for each one of these. So, yeah.
My question is like, one of the problems that you said was we don't know the size, like the length.
Yeah.
But in this case, wouldn't you need as many as the outputs?
Yes, we would. So you need as many weight sets as the output sequence, and we will address that problem as well. So, but if we have something of this kind, then the problem is simple. Solution is simple, right? You'd have one set of weights for the first output word, and you'd be averaging all of the hidden representations on the input with that set of weights for the first word. Then you'd have a second set of weights for the second word. And so you'd be computing this weighted average with the weights corresponding to the second word to generate the vector C, which is called a context vector, just for terminology. And the context, it's again, we're always dealing with this as a language generation problem. The decoder is always a language generator. It's a language model. What is happening over here is that in the generation of each word, we are using a context. And the context is being driven being obtained from the input side, from the encoder, right? And so the context C1, which is used to generate the second word, is going to be a second word specific weighted combination of the inputs. And so also for each of these output words. And we'd continue generating stuff as always until you generated an end of sequence marker. So question now is, where do these weights come from, right? The requirement we have is that the weights must be specific to the output. And the question is, what is the mechanism, what mechanism can we use to obtain such weights? Now, these weights are what we call attention weights. So when you compute a weighted sum of the representations on the input side, the weights are figuring out which portion of the input must be attended to in generating any particular output. So here, for example, when I'm generating ish, the weights must somehow tell my model that I is more important than upfill, right? On the other hand, when I'm generating, when I'm trying to compute or output the word upfill, it must know that the word apple on the input side is more relevant to this particular output, and somehow compute the weights in this manner so that it can obtain the right context to generate the word apple. And so this computation ends up being key. Now, how can we compute these weights? Yes, Chetan.
Are we taking the pretty sum of the hidden states themselves or the output to
The hidden states themselves over here, right? So just the h's. And so look at what the context vector is. It's basically a weighted sum of the h's. So in this case, I have 1, 2, 3, 4, 5 h's corresponding to I ate an apple end of sequence, right? And so the context that is used to generate, that is used in the generation of any word, is a weighted sum of these 5 hidden states. That answer your question? Yeah. So now let's look at what we can use to compute the weight at any time. So let's say I'm trying to generate the 4th word in the output. When I'm generating the 4th word in the output, I can only use information that I have already computed so far. There's no other information available. So although I'm trying to generate the word apple, I don't know that beforehand, right? All I have is everything else that has been computed. And what has been computed so far? The hidden state at the previous time. So you have S2 that has been computed. S2 is the S's are the sequence of hidden states on the decoder side. So S2 has been computed. And so the only thing that we can use, also, we could technically also use this word einen. So S2 and einen are the only things available right now. And we must use these somehow to figure out the weights of the terms on the input, which means that the weight for, say, I must be a function of H0 and S2 and einen. Typically, we will not consider the word itself. We'll just use S2, right? And so the weight for, say, for each one of these input words is going to be a function of the corresponding hidden state over here and the S, the decoder hidden state at the previous time. That clear? Questions? Yeah.
Just to clarify, so for the C3, that is for the attention for the next word, we use the previous the previous hidden state and all the input hidden
Yeah,
states.
everything that has been computed so far, right? That's all you have access to. You have nothing else. And so the weights that we will use to compute C3 are going to be a function of S2 and the individual hidden states. Now, we have some more requirements on these weights. The weights cannot be unbounded, because if the weights are unbounded, then the weighted sum can just blow up or just vanish, or it can there's no restriction on how the context on the context vector itself, right? So we would like the context vector to look somewhat like the hidden states on the encoder side to begin with. And one way to ensure that is to ensure that the weights are all the weights sum to 1. So you get a weighted average, a convex combination of the hidden states on the input side. So you want the weights to be positive, and you want the weights to sum to 1. Now, what kind of function will give you a bunch of weights that are positive and sum to 1? A softmax, right? So in this process, so basically you want the weights to be a distribution, and the weights to somehow highlight the appropriate words on the input side. And so the way we do it is that we use a two-step process. In the first step, we are going to compute a raw weight for each of the terms on the input. And the raw weight is a function of the hidden state on the input side and the decoder's hidden state. So the raw weights for each of the 5 words over here are going to be a function of the corresponding H and the S at the previous time on the output side, right? And then once you have computed all of these raw weights, you can just put the whole thing through a softmax. And so now you get a distribution over all of the inputs. And this has all the necessary properties. And to answer your question, Vibhai, this actually automatically accounts for the length of the input, right? So yes, Chetan.
And then would you also assign a weight to the previous decoder hidden state?
No, this is everything is just coming from the encoder at this point. Because you're just trying to figure out, again, remember, the point is we're treating this as a language model, right? So this is an autoregressive language model, just like we saw in the last class. So each word is being produced conditioned on all the words that it have been produced so far and some extra information. And that extra information is being derived from the encoder, from the input. So the dependence on the previously output words is already in the model itself, right? There's a poem. Time's up. So Pokemon Larvitar, Heiji Jung, what's the answer to the first question? True. Pokemon Clefairy, that's you, Katrina. False. And Pokemon Makuhita, that's Sujin Choi. What's the answer to the third one? Pokemon Makuhita?
Is true.
So everybody agree with those answers? The first one is true. The attention framework computes a different context vector at each output time. This is chosen as the, this is not chosen as the hidden representation with the highest weight, although in principle you could actually try that. It wouldn't work too well, right? And the attention weight to any input word is a function of the hidden encoder representation of the word and the most recent decoder state. So all good. And so here's where we are. In order to generate any output word, we're going to compute a context. Again, the decoder is a language model. I cannot emphasize this enough, right? The decoder is just, the reason we started with speaking about language models is to teach you the idea of a statistical model for language. All this is a conditional statistical model for language. And it's going to be conditioned on whatever you saw on the input side. And the manner in which the conditioning is applied varies from output word to output word, right? And so in order to generate any particular word on the decoder side, you're conditioning it on some weighted sum of the inputs. And the weights are computed to be a distribution. So of course, there's a two-step process to computing these weights. First, you compute some raw weights, and then you compute, put them through a softmax. What are these raw weights? So there are a bunch of different possibilities that have been considered. Now, if the decoder hidden state and the encoder hidden states are the same size, then the natural thing is to just look at the inner product. Do they align, right? Now, if they're not the same size, then you can match up their sizes by having an intervening matrix, which brings the size of one down to the size of the other. And that matrix is something that could be learned. Now, there have been uglier functions proposed as well, such as this one over here, or even having an entire MLP, but they're not very popular because having this extra work being performed in the computation of the attention weights has not been shown to be particularly, give you any particular advantage. So we usually stay with the simpler ones, right? And so let's see how a typical conversion process, assuming the matrix in a product as our mechanism for computing raw weights, would work. So the input would go in, and your recurrent model would compute the hidden states for every one of your input words. This would proceed until you hit the end of sequence marker on the input. Subsequently, now the decoder is a recurrent model in our setup, right? You're going to need an initial state. Where does that initial state come from? Now, unlike your standard recurrent networks, this one ends up being important for a very simple reason. That is that this hidden state is actually going to determine how you pay attention to all of the words in the input, right? So there are a bunch of different options over here. You could learn this. You could just set this up to be all zeros or all ones. Or better still, think of this as some weighted average, or as the average of all of the hidden states on the encoder side, or something that transforms the average to the correct size by some initial matrix operation, right? So I could just look at the mean of all of these guys, and that could be by s minus 1. But if that's not the right size, then you could bring it to the right size with some w in it. Regardless, there are a bunch of different options, and depending on the manner in which you set this up, the mileage you might get in recovering the initial words of the output sequence could vary, right? Once done, you can just use that s minus 1 to compute the attention weights for all of the hidden states on the input. And the way you would do it, of course, is that you're going to compute the raw attention weights which is just the matrix inner product between the hidden state on the encoder side and s minus 1, and put those through a softmax. And this softmax is going to give you a bunch of weights which are specific to the first output. And you would use those weights to compute a weighted average of all of the encoder hidden states. And that's going to give you the first context vector. That first context vector goes in. And now the decoder is going to compute a probability distribution on the outside, right? From which you would draw a word using some mechanism.
Prof, there's a question on Zoom.
Yes.
If there's a different language where the order matters, what changes in the step of attention?
So does it different?
If there's a different language where order matters, what changes in the step of attention?
Absolutely nothing. So the order does matter, right? I ate an apple. I'm not sure. So I'm not clear what the question is, because in everything that we've looked at so far, the order has mattered. Can you repeat the question? Maybe restate it?
So if we're talking about a different language, like where, for example, not for German, for example, maybe for Arabic or for any other language, where the translation could be different in sort of order. So what changed?
The process doesn't change one bit, right? The whole idea is that the model figures out how to do the right thing. So the manner in which the weights are computed is still exactly the same. Nothing changes.
Okay.
Right? And so from this distribution, you would draw a word. And the drawn word is going to go in. Now, in the process of drawing the word, you have also computed the hidden state at time 0. And so that hidden state at time 0 can now be used to compute the raw weights for time 1. And then those raw weights could be put through a softmax. And now you'd use those. And so that's going to give you a bunch of attention weights, which you could use to compute the weighted sum of the weighted average of all of the hidden states on the encoder side. And this gives you the new context. And that new context is now going to be used to generate the compute the next output distribution from which you draw the second word. And so this process would continue, right? At each time, you're going to use the most recent hidden state at each time t. So now there are two distinct times. There's the time, input time, which is completely different from the output time, right? Here I have input time going from 0 to 4. Output is going, something else. So I probably shouldn't be using the word time. They just sequence indices. They're two different sequence indices, right? And so at each output index, you're going to be using the hidden state at the previous output for the previous output to compute the raw weights, and from those, the attention weights themselves. And those you would use to compute the context. And this would continue all the way until you actually generated an end of sequence marker, right? So the process is very straightforward, nothing particularly complicated. Everybody clear with this?
I have a question. What is G, the function G?
So the function G, okay, I only mentioned that in the very first slide right here. In this case, we're just assuming, G could be anything, but if I were using a matrix in a product, assuming that the hidden state vectors are different lengths in the encoder and the decoder, then you're going to need a matrix to match the two sizes up. And so the function G between any HI and SJ is going to be HI transpose WG SJ, where WG is the matrix which brings each vector down to the size of the other. That answer your question?
Okay, not exactly the mathematical representation. I mean, like, what is the significance? Like, what does it do?
So the function G basically is checking how much. Again, what does an inner product do? It's really checking an alignment, right? So the inner product is determining how much S2 aligns with each of these hidden states. The more it aligns with something, the closer its dependence on that particular hidden state is likely to be, right? Or the closer the dependence of the next word on that particular hidden state is going to be. That's the assumption here. So if you wanted to plot these things up, you could just plot all of these as vectors. And the H vector that any S is closest to in angle is going to be the one that you would think is most relevant. Did that answer your question?
Okay, thank you.
So there's a reason we work with inner products. There's a certain degree of interpretability to it, right? Anyway, so here's the whole process. This is what we call attention-based decoding, where the attention came in is the computation of these weights at each time. And these weights determine how much attention is being paid to any given word and the input. So I can make a minor modification to it. The way I've done it over here, I just said we're going to use the H and the S directly to compute the attention weights. But then think about the simple process of, Ich habe einen Apfel gegessen, right? When I get to the word apple, then, or when I get to the word einen, is it particularly relevant that this word is an apple, specifically an apple, or is it sufficient for me to know that it's something that's edible? What would make more sense to decide what to pay attention to? The apple is not competing against an orange over here, right? If I'm going to be eating something, the fact that it's edible is all that I really need to decide that this is what I must be paying attention to. On the other hand, when I actually perform the translation, I need to be very clear that this is a word apple that I'm translating. So there are two different operations require two different levels of granularities of of characterization, right? In order to figure out what component of the input to pay attention to, I just need broad categorical information. But to actually figure out how I'm going to attend to it, I need the detailed information. So we sort of like to decompose this into two different operations. From each input, from each of these hidden states, we compute two terms. One is something called a key, and the key gives you the the lower granularity representation. It would tell you that this is something edible. The value says that this is specifically an apple. And so you're going to use the keys to decide what to pay attention to, but then the actual context vector is computed using the value. So there's this key value, query key value decomposition, which is commonly done, that from each hidden state, we compute two terms. One is the key corresponding to that hidden state. The other is the value, and both of these are just linear operations. Again, the key is more granular, right? So in terms of your expectation, which of the two would have the higher dimensionality? The key or the value? The value, right? The value is saying this is an apple. The key is just saying this is something that can be eaten, right? Or maybe it's a fruit. And so correspondingly, you could have on the decoder side, a projection from the hidden state down to a query vector, also done by a matrix. And now when you actually compute the attention weights, you're going to use the queries and the keys to decide the attention weights. But then the context is computed as the weighted average of the values. So the key gives you the crude level coarser information, right? So you're going to use the key to decide the attention weights for each element. But then once you've decided the attention weights, what you will actually pay attention to is the value. So you're going to be using the Q's and the K's to compute the weights. But once the weights are computed, you're going to be computing a weighted average of the V's. Make sense? Right? So again, you expect the K to have a coarser, represent information at a coarser granularity than the V itself. Now, this is how it's normally implemented. In our, so our raw attention weights are now going to be functions of the key and the query, but the actual context is going to be a weighted sum of the values, right? In the examples that I've used so far, we didn't actually show this decomposition, so we just assume that the keys and the values are the same and the query is the hidden state itself. So I'm going to continue using this illustration for much of the remaining slides, but then you must always remember that this additional step is often implemented and it makes sense, right? Intuitively, it does make sense. Yeah.
So the computation of the key and the value is two separate parameters that we have to.
So from H, I'd have two different matrices. One of them is going to compute the value. The other is going to be computing the key.
And those are both learnable parameters.
They're both learned parameters.
And then we just like hope that they'll learn that one will be like and then we specify that one is more granular than the other by just the size of the matrix.
Yeah. And hopefully they learn the right thing, right? Okay. So now going back, we saw the procedure, the process that's being followed. But then if you go back and look at the math, this is still a language model, right? And this is still trying to draw an output from a distribution, which is specifically the distribution of all the words in all word sequences in the language, conditioned on the input. So this is a conditioned language model, right? Which means that you really want to be drawing an output sequence. If you're performing something like translation, you specifically want to be drawing an output sequence that is most probable, right? And this again means that you want to draw the sequence of symbols O such that the product of their probabilities is largest. And this is complicated by the fact that it's autoregressive, that each output goes back into the network at the next time. So, if you draw something wrong at this time, then your future is destroyed, right? And so we couldn't actually commit. We didn't want to commit early. And when we encountered this problem in the last class, how did we deal with it? We do a beam search. Now, except that things get a little more complicated. The way we did it in the last class, there was once you just perform the encoding, we got the final hidden representation, and things are not, you didn't go back to the encoder at each decoder step, right? But now, because at each decoder step, you have to go back and derive a context vector from the encoder side, the beam search becomes a little more complicated. Now, of course, the cheap solution is to maybe always be greedy and just draw the most probable word, or maybe do something random and just randomly choose a word. But if you want to be more optimal, then you actually want to do the full, expand the tree out and perform beam search. So here's what we would do. You'd have the encoder. Now observe that the encoder is completely diverged from the decoder. You can just perform the encoding, and this encoding doesn't pass any information on directly to the decoder. The encoder and decoder are two distinct components, right? So as far as the decoder is concerned, the encoder is just some box which generated a bunch of vectors, one corresponding to each input word. And so now the decoder is just figuring out how to combine those for each output step, right? So the encoder has done performing its computation. And then at the very first step, you'd compute a context vector by as a weighted combination of these hidden states. And that's going to be passed in to the first decoder step, which computes probabilities for all of the words, right? And then each of those words could then potentially be fed into the decoder step here, except that in doing this, now we are going to need to actually use this hidden state to compute the context vector, right? The context vector is common for all of the copies in the second column, because the context vector is always computed using the previous hidden state. Nonetheless, you would have to compute it, right? But even before you do that, you don't actually have to expand it out with every possible word. You're performing beam search. So you just retain the k most likely or the most probable words over here, and only make k copies of the decoder, and each of those would get one of these words as input, right? And moreover, each of those is now going to get a context vector which has been computed. So it would be a single context. Yeah. You don't need two context vectors. There's just one single context vector. The figure's a little erroneous, but because you're using this hidden state to compute the context vector, you'd be computing a single context vector which goes to both of these guys, right? And now at the next step, these can be expanded out, but you're going to only retain the k most likely, right? And so those can now be expanded. And now each of them has a different history, right? Each of them has a different history. And so because of that, the context vectors being computed for the elements from the branch above, and the context vectors being computed for the elements from the branch below are going to be different. So you'd have to compute the context vectors twice. Now, when you're choosing the top k, you're going to choose the top k based on the total probability of the entire path from the beginning to the latest word, and not merely based on the last word that you see, right? So the top k are going to be chosen based on this product, which is the product of the probabilities going all the way to the beginning. Which means that although some word might be highly probable in the upper path, it may still get pruned out when it's compared to some locally lower probable word in the lower path, because the path level probability was higher, right? So at each time, you're just going to retain the top k scoring folks and continue this until you eventually hit an end of sequence marker that is which gives you a word sequence that's more probable than anything else that you have retained. And that's when you're done, right? So does that make sense? Any questions?
Why are we using different context vectors for both of them? Aren't they at the same level?
So here, for this guy here, for instance, this would be the hidden state, right? This is what is being used to, can you see my pointer?
Yeah.
So this is what is being used to compute the context vector for this fellow, whereas this is being used to compute the context vector for the one above. So the previous hidden states are going to be different, right?
Why are they different for those states in the first place?
Because you come down different paths. So this one went this way. So if you go back here, at the very first time, they all have the same hidden state. So they would all have the same context going in. And now the hidden states computed here and here are going to be very different because different words went in, right? The first one saw the word he, the other one saw the word thee in my example. And so these hidden states are now going to be different in these two cases, correct?
Yes.
And so correspondingly, the context vectors here are going to be different as well.
Okay.
Answer your question?
Yeah.
Yeah. And so you'd continue this all the way till the end. So now, does this really work? For this to work, we are sort of hoping that this mechanism we chose to compute attention weights really does the right job. So what do these attention weights look like? The attention weights capture the relative importance of each position of the input to the right, each position in the input to the current output. So here are some examples from the first paper by Badanav et al. They use this for machine translation. And the figure here shows, so the input is in English, which is shown on top. It's being translated to French, which is being shown on the side. And each row shows the set of attention weights that was used to compute that the word that's being shown on the left. So here, for example, the English sentence is the agreement on the European Economic Area was signed in August 1992 period, end of sentence marker. And the translation was l'accord sur la zone économique européenne, blah, 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 right? My French pronunciation is awful. But anyways, so in generating the word le, those are the attention weights. And you can see that it automatically figures out that the word that it must pay most attention to is the word the. That's what is brightest, right? The second word is accord, which corresponds to the word agreement. And once again, when you look at the attention weights, you can see that in the second row, it pays most attention to the second word, right? Agreement. And the word sur corresponds to on. And so it actually pays most attention to on. And the la corresponds to the, so it pays most attention to the word the. And then the next three words are more interesting. In English, you'd say the European Economic Area. But when you take this to French, the word order is swapped. It's Zone Économique Européenne, right? Zone actually corresponds to area. Economic, of course, is economic, but European is European. And so if you look at the attention weights, it actually figures out what it must pay attention to. So the attention pattern is not diagonal. It's diagonal until it hits this little patch, and then it flips order so that it actually captures the inversion of order between English and French. And then once it gets past that, there's a little bit was signed in, it's signe, that's a bit mixed up, and then it goes back to being diagonal, right? So this model actually does seem to capture the kind of attention patterns that you would expect it to capture if it's learning to focus on the right words on the input in generating any output. Let's look at any other example. This will change. I could do a better job of explaining these things if I knew any French. I don't. But in every example, you're going to find that the attention weights actually seem to figure out what to focus on. Does anybody here know French? Nobody? Too bad. Right.
I know French.
Okay. Can you tell me if the attention patterns in the second figure make sense? Do they?
Can can you zoom a little bit? I can't
So,
really see the words.
so the first one is, it should be noted that the marine environment is the least known of environments, period. And then the French, I'm not going to even, I'm not brave enough to try to pronounce it. I think the first one is ill.
Il convient de noter que l'environnement marin est le moins connu de l'environnement.
Fantastic. And do the attention patterns match?
Not completely. Yeah.
Well, I'm assuming that they're somewhat right. Okay. Yes. So,
Like the single English environments gets le and environnement, you know, like able to understand that the single word environments corresponds to the two.
beautiful. See, there you go. So it actually works, right? And here there are some translation examples. I am informed by reliable sources that these translations are very good. Now I'm going to place my faith in whoever said this to me, and so they're very good. Now, just to set you some, give you some context, just before this paper came out in 2016, the best machine translation systems of the day were pretty horrible. If you translated from English to French and went back to English, what went in and what came out would not even be in the same universe very often. And suddenly, literally overnight, they began using this attention-based translation system, and things just worked, right? And they've gotten much better since. So we've seen how a trained network can be used to convert inputs, convert one sequence to the other. Now, what about training itself? Now, when you're performing training, you're back to this old problem. There was a problem that well, there was something I mentioned in the last class. There are two ways of thinking of the process of training, right? And this has to do with the two different perspectives that you can have to the model. What were these two? What were the two perspectives? I mentioned this in the last class.
I don't remember it fully, but I think you said you would either compute the divergence over the entire sequence, or you do it step by step.
No, so the two different perspectives are that you can either think of this as a language model, which is being conditioned on the input, or you can think of it as a box which takes a sequence and generates a sequence, right? So if I'm thinking of this as a language model that's conditioned on the input, then here's what I would be thinking of. The output is going to be, how did we train a language model? When we trained the language model, you were given a sentence, and then at each point, you assumed that you knew all the words until that point, and you were predicting the next word, right? So this was your standard maximum likelihood estimator. You were always thinking of predicting the next word. The only difference over here is that in addition to predicting the next word, you're also conditioning it on the input, right? Now, so if that's what you did, your training sequence data are going to comprise pairs of sequences, the input sequence and the target output sequence. The input sequence would go into the encoder. Then the target output sequence would go into the decoder, one word at a time. And at each time, the output, the decoder, would see the sequence of words until the latest word here, which would be upfill over here, and the targeted prediction would be the next word upfill, right? So on the output side, you'd be seeing words W1 through WK and trying to predict WK plus 1 at each time. And of course, you can compute the divergences at each time and train this in much the same manner that you would train a language model. It's going to be the sum of the divergences for each of the words. And this loss can be back propagated to update all of the components of the model, both on the encoder side and the decoder side, right? Now, and in the process, if you have some function G, which could be a matrix in a product, then the parameters of G are also going to be updated, right? So this approach basically performs maximum likelihood estimation of the model. And that's because you're treating this as a conditioned language model, right? And it kind of makes sense. If I think of it as a conditioned language model, it makes complete sense. But there was the other way of doing it, which we mentioned, which was that instead of thinking of it as a language model, you can just think of it as a black box, some network where an input sequence goes in and an output sequence comes out. And in this case, what you would be doing is feeding in the input sequence, getting an output sequence, comparing it with whatever loss to your desired output sequence, and that loss, the derivatives of that loss, will be backpropagated. And what was the problem with trying to do this in the more traditional way? We mentioned this in the last class.
Divergence for the sequence.
Computing the divergence for the sequence. Yeah, yeah.
Is that like, you don't, like, because the length of the output and input?
They may not match, right? The output could be complete garbage. So in this traditional mechanism, you would be just generating the output. You'd be comparing it to the target output. And the problem, of course, is that this wouldn't work because in the initial portion of the model, in the initial iterations, you have absolutely no control over what's going to be generated. You could get pure garbage, right? How do you actually compare something like that I have on the screen to your target output sequence? You cannot. They are not comparable. And so computing a loss is going to be challenging, to say the least. Yeah.
Can you explain that first training? Like, one more time.
So here, what you would be doing is this. You would pass the data through the encoder, so you get all of these hidden state values. Then at the very first time, you'd be passing in start of sequence, you get an output. You'd be comparing it to the word ish. Then at the next time, you'd be passing an ish over here, get an output, you'd be comparing it to the word harbor, and so on. This is like training a language model, where you're giving all the words until the next word, until the current word, and trying to predict the next word, which keeps getting updated as you go down the sequence, right? Whereas here, so what this means is that in the process of training, you're feeding in both in your conventional process of training, you fed in the input, the output didn't go into the model. The output was only used to compute, the target output was only used to compute the loss. Whereas here, you're not only feeding in the input, you're also feeding in the target output to the model, right? And so in the traditional training sense, it's a bit like cheating, where you would be telling the model, here's what you must generate it, and obviously it's going to do it, right? So it looks a lot like that, but then I can explain it off by saying this is just a conditioned language model. Does that make sense?
So it's like a bit different because here we're using the previous to like get the next one.
So that's correct. So this is the conventional one, right? In this conventional approach, the D only goes in to compute the loss. Whereas in this approach, we are giving it both the I and the D, and it's generating the Y, and then you're comparing it to D. So the desired output is also going in, being fed in as part of the training. You see the difference, right? So in some sense, it's a little cheating, in the sense that you're telling the model what it must generate and checking if it's indeed generating it. So
maybe like feedback some word from random.
that's exactly what we do, right? So clearly, what we want to do is this, but this is not going to work. And the biggest challenge here is that you don't have any kind of one-to-one correspondence between what it generates and what it must generate. And so, and we try to find a midway solution. So when we actually feed in the target output along with the input, The target output is in some sense teaching the model, right? So the terminology they like to use is teacher forcing, where the teacher is giving the student the answer and then beating the student to regenerate the answer. But now this is much more controlled because you have a one-to-one correspondence between what must be generated and what it does generate. And the midway solution is that instead of giving the entire input sequence, you drop parts of the input sequence here and there. So for example, you might just say, I'm going to give you start of sequence ish harbor, then I don't tell you the next word, then upfell and gig is in, right? And in the process of learning the model, for just that word where I have the stars, the actual output word is not provided. Nonetheless, the actual input word is not provided. Nonetheless, you must predict the next word, right? So it's kind of half-assing it, but it's better than not providing, better than cheating all the way through, right? Yeah.
So you would just feed in the S2 output into.
Yeah, the S2 is going to be used to compute the context nonetheless, right? That doesn't change. So the typical mechanism that you would use in a situation like this is that you would start off with this fully teacher-forced, because we don't like to call it cheating, right? Teacher-forced method, where you're treating it like a language model. And then as the model gets better and less likely to produce pure garbage, you begin dropping things on the input and let the model generate the word on its own. And of course, when you're doing something of this kind, you have a problem. One of the steps here is drawing a word from a distribution. And the process of drawing a word from a distribution is not differentiable. So which means that if you want to pass, this is a selection of a word from a distribution. If you change this, the output would change. So there is an influence. But it's not differentiable in that there's no such thing as perturbing a word a tiny bit, right? This doesn't happen. So we have to use some kind of a trick to pass the derivatives backward. And the way you would do it is to think about it in terms of, say, the embedding, right? What happens if I change the embedding a little bit? We begin working at the embedding level. But more mathematically, you like to think of something called a Gumbel noise trick. Now, again, a Gumbel noise trick is based on a very simple principle that if I have a probability distribution that I'm trying to sample from, so suppose I have a probability distribution P1, P2, P3, Pn. So there are n possible outcomes, like an n-sided die. And these outcomes have different probabilities. I'm trying to draw a sample from it. So most of us, if not all of us, know how to write code to draw a sample from this, right? But that process is not differentiable. So it turns out there's something called a Gumbel distribution. And so a Gumbel distribution is, I'm just going to call it G. And it generates values between 0 and 1. I can just draw a random vector from the Gumbel distribution. And that's going to give me some G1 through Gn. And to these, I can just add log of P1 through log of Pn. And then if I find perform an argmax on this one, it turns out that the distribution of the argmaxes of these vectors will be the same as P1 through Pn. That's just a property of the Gumbel distribution. And so because of this, I have replaced the process of random sampling by the process of argmax. And the process of argmax is basically going from here. Now, again, we're not really interested in the argmax. We are sort of interested in a mapping which goes from here to a one-hot vector, right? Which gives you a 1 at the location of the word that's drawn. So how would you convert this to this? You can just put a softmax on it, right? So it's not going to make it a hard, one-hot vector. but it's going to make it a soft one hot vector. And so now that soft one hot vector can be used instead of the one hot vector on the input, and now derivatives can be passed backwards. So that's a trick which allows you to differentiate through a sampling process. Yes.
I don't know, this may be a fundamental question, but since we're computing the divergence at every time step, as in like we're computing the loss between the target input at that step and the generated output at that step, why would we need to backpropagate based on the sampling, since we use that only for inference?
The point is you always want to propagate all the way backwards through the sequence, correct? So this is something that we always needed to do. If you want to say something that you do now could have an influence 10 steps into the future. And that's why we always want to propagate. This was why we wanted full recurrence as opposed to the partial recurrence, going back many classes, remember?
This will influence the hidden state, and then that.
Yeah. So, well, in practice, we actually wouldn't bother to backpropagate derivatives through that sampled word, because it's often the added complexity is not worth the trouble. But if you wanted to do it, this is the way to do it. It actually convert the process of sampling to generating to an argmax over a vector, which is obtained by adding a randomly drawn sample of collection of numbers from a Gumbel distribution to the log probabilities. And the argmax can be converted to a softmax, which is differentiable, right? So now this is the basic idea. We've gone through the whole attention framework, and that's the basic idea. Now there are various extensions to this. The encoder side could be using a bidirectional network. You can't do this on the decoder side. Why? You don't have the future. It's autoregressive, right? And then you have various variants on the attention, local versus global attention. If the input is too long, if the output is too long, how much can you pay attention to? So there are variants to it. And then also, there's something called multi-head attention, which is based on the idea that different portions of the input might have different kinds of relevance to the output. So instead of deriving just one context vector from the input, you might want to derive multiple context vectors from the input, which means that corresponding to each context vector that you derive, you're going to have its own set of keys and values on the encoder side, and its own set of queries on the decoder side. And then so from each set, you'd get a different context vector. It's called multi-head attention. Yeah.
Is this the same as like if you have a convolutional neural network, you get like the larger like the filters at the beginning versus at the end get like more broader features?
No, not really. This is more like saying that there are two different reasons for me to be paying attention to something, right? One is this a fruit? Or is this edible? The second is this a noun? They're two completely different categories. They're two completely different views that I can take to the input to decide what I must pay attention to. And so each of these heads can be thought of as using one particular view to decide on attentions and to derive a context, right? So here's the second poll.
Time is up.
Okay, time is up. Pokemon Pidgey. Malachi, what's the answer to the first question?
The first question is food research.
Thank you. And Kombuskin. Hiesu Lim, what's the answer to the second one?
Second one and the third.
So, wait a minute. The second and the third are true, right? Full tree search is what you would have to perform to be fully optimal. And in multi-head attention computes a separate set of keys and values for each head. And it also computes a separate query on the decoder side corresponding to each head. And the different heads may be thought of as computing different views of the input to decide to compute a context vector, right? Questions, anyone? Yeah.
So, like, continue the CNN analogy, is that like different filters then?
You can think of it as different filters, that's correct. Yeah. How many heads are common, guys?
How many heads are?
Commonly used.
8 for bird, I guess.
4, 8. More than one, right?
Yes.
So, anyway, lots of really good results. Because attention-based models are the state of the art in pretty much everything in the universe. Attention has replaced every other kind of computation these days, although we are finally beginning to go back to look at the older kind of convolutional and recurrent models, because it turns out that maybe they're not so bad at all, right? So it's used for machine translation, used for speech recognition. Machine translation, English goes in, French comes out, speech recognition, speech signal goes in, text comes out. You're going to do that in your homework. You can have dialogue systems. The user's input goes in, the system response comes out, and so on. And they also have shown that the same mechanism now works for other things like images, right? So we do this all the time. Here in this example, the images have been analyzed using a convolutional neural network, which means it's going to get a vector at each location, right? When you convolve it with a bunch of filters, at each position you're going to get a vector. And now the decoder is learning to pay attention on this collection of vectors on the input side to generate its output. And so here you can see, for example, when it captions the first picture, a woman is throwing a frisbee in a park. If you look at what it's paid attention to generate the word frisbee, it's looked at all the pixels that sort of lie around the frisbee, right? A dog is standing on a hardwood floor. Sure, it got most of the caption wrong, but when you look at what it's paying attention to when it says dog, it got the dog. A stop sign is on a road with a mountain in the background. It got the stop sign, right? A giraffe is standing in a forest with trees in the background. That's the most interesting one. When you look at what it's paying attention to, when it says trees, it's paying attention to everything except the giraffe. It is, quite impressive, right? And so on. So the model is really good. Anyway, we've looked at various forms of sequence-to-sequence models and generalizations of recurrent, which are generalizations of recurrent formalisms. And if there are lots more details, there's so much work on this that I can't even begin to go there, right? You can post questions on Piazza, and homework 4, and those of you who are doing homework 5 are going to encounter this quite a bit, right? Now, this is the recap, right? In the simple translation model, the hidden activation of the end of sequence marker captured all the information about the input. This wasn't so great. So in the attention-based model, we tried to pay attention to everything on the input. Now, for the next 10 minutes, I'm going to be talking about something that we will be covering in the next class. But this is just to give you an idea, right? Here, if I'm learning to actually pay attention to the right word on the input, why do I need recurrence on the input? Do I need recurrence? What is the problem with recurrence on the input over here?
Have to do it sequentially.
The problem with recurrence is that the I is going to be influencing Apple, right? The representation at Apple is going to have some little bit of I, regardless of how you do it, right? And considering that and the original intention of having recurrence in the simple translation model was that you really wanted this. You wanted all of the information towards the end. But when you've given up on that and you say, I'm going to individually pay attention to every one of the words in the input, do I really need this recurrence? I don't, right? So what if I get rid of it? Would this work? It should work, right? But this is still not quite there. What would be the issue with something of this kind? The order, well, the order is one, and the other, the interpretation of any word really depends on the context, right? I don't know whether apple is a computer or apple is a fruit. To figure out whether I'm talking about the computer or the fruit, I have to look at the rest of the sentence, and I got to figure out that, it says 8 and not programmed on, right? So for that information, something that is looking just individually at each word is not going to capture it. And so how can you solve this information, solve that problem? I want the representation for apple to consider the fact that somewhere in the sentence there was an 8. Yes?
Can you, instead of just like having recurrence in the hidden states, just feed in all the inputs to like successive, like as in like H1 now will take in both I and A.
Something like that, right? So if I just get rid of context, this recurrence, I'm going to eliminate context specificity. And this is a problem, right? So, the word apple, is it a computer? Is it a fruit? I have to look at the rest of the words in the sentence. And how I can do this is to use attention itself. So here's what I would do. I'm going to, on the encoder side, I can get rid of the sequential nature of the model, but I can still retain context specificity by using the attention framework. This is what we call self-attention. So the way it would happen is like so. I'd just compute an initial representation for all of the words. Then, from each of the words, I would compute an updated representation. And the updated representation is going to consider all of the neighbors. And so in order to do this, from each word, I'm going to be computing, just as before we computed a key and a value, and on the decoder side, we computed a query. Now, this little row itself is both encoder and decoder. So from each word, I'm going to be computing a key, a value, and a query. So the key, again, as I said, is a coarser representation than the value, right? And then the query is, what do I look for in my neighbors? And subsequently, if I want to just update my representation for the word I, I'm going to use the query for the word I and the keys for all of the words, including I, to compute attention weights for all the words. So I'd be using Q0 with the keys for every one of the words. And so when I compute attention weights using Q0 and all the keys, I'm sort of going to learn the relevance, or again, remember that when I'm looking at something like a matrix in a product, I'm looking at vector level similarity, right, closeness. So I'd get some idea of how close this word is to each of the other words in my sentence. And from those, I'm going to get a bunch of attention weights. These attention weights are specific to the first word in the sequence. And then using those attention weights, I can compute a weighted sum of all of the values of all of the words in the sequence. That's including itself, right? And so now this is going to be my updated representation for the word I, where in trying to represent I computed an initial representation. From the initial representation, I computed a keys, queries, and values for all the words. I used the key for the word I and the query for the word I and the keys for all of the words, including I itself, to compute a bunch of attention weights. And then using those attention weights, I averaged the value vector to compute the updated representation for I. I can do the same thing so that's my updated representation for I. I can do the same thing for every one of the words in my sequence, right? And so now I have updated the representations for all of the words in my sequence. And the updated representation, hopefully, has managed to consider the influence of all of the remaining words in the sequence, right? Now, at this point, it becomes a little bit of engineering. So this is our self-attention module, right? And typically, this is what is a single head self-attention. And again, if you're doing this with one head, as before, you can do this with many heads, right? So you typically do a multi-head self-attention. And then you're going to get an updated representation based on every one of these heads, which you would concatenate to get the updated representations for all of the words. And then just to mix them up, typically you throw in a single linear layer with possibly an activation, a little MLP, so to speak. And this is what is going to be a multi-head self-attention block. So what we have done over here is we've gotten rid of recurrence, but then because recurrence runs this risk that getting rid of recurrence runs this risk that you lose context specificity for the representations. You're using attention itself to draw in the influence of the remaining words in the sentence to update any particular word. And simply because doing it once is not sufficient, when you're doing something of this kind, typically you have many layers of this to make sure that it's properly, that the representation that you get is properly aligned with the rest of the sentence. Now, in all of this, you're still losing one little factor, which is relative position, right? A context word, which is one word away, is got a very different interpretation than a context word that is 10 words away, right? So if I want to keep the notion of how far the words are with respect to one another, how could I do it? I can just drop in the index for every word, right? So earlier, I could have just said, so I had word 1, word 2, word 3, word 4, and so on. I could just add 1, 2, 3, 4, add the indices over here as an extra term. Now, just having an index of this kind, it turns out as an issue in that you're not going to learn very much about 4 from anything that's not 4. So here's a somewhat different way of thinking about the whole thing. Instead of just having an index, I can think of this as a binary representation. So let's say I'm going to use 4 bits to represent the index, right? So the first guy is going to be 4 zeros. Or this actually, if I'm starting at 1, it's 0, 0, 0, 1, right? 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. I'm still using just the index, correct? I've just represented this in binary. But then what do we observe about each of the bit sequences? So this one here, if you look at this, this is simply going to be something like that, correct? This one here is going to be something like this. This third one would be so each of them is basically going to be a binary sequence, and each one is going to have half the frequency of the one below it, right? Now, this ends up being very restrictive because the whole point is you want each vector to be unique, right? And if I'm using 4 bits, then after 16 vectors, things are going to begin repeating. So we convert what seems to be just a square wave into something that's a lot more complicated, which is based on sines and cosines, which have a very, very unique property that the manner in which we compute this vector has the property that the relationship, the arithmetic relationship between two vectors is a function only of the distance between the two vectors and nothing else. And so these are positional embeddings. I'll stop right here. And so this was just to give you a sort of a preview onto how we can go past recurrence and actually begin using attention itself as a replacement for recurrence, and how you can factor in context specificity and the positionality of words in the process. We'll pick this up in the next class. Thank you very much.